Hello, everyone. This is Kenan, and I'm a PhD student at Izmir Democracy University. In here, I'm presenting a final project for the subject called, or the course I'm taking, machine learning course, delivered by Associate Professor Dr. Binullah. Within this work, I am trying to understand the effects that we can get when we change the learning rate on the accuracy and loss plus the performance of a model when we do image classification. So maybe I'm focusing on the learning rate effects on the image classification model. All right, so let's get to the content. The content that I'm going to present is, first I'm going to start with a problem, and then I'm going to propose a solution to the problem. I'm going to present the data that I will use for the model, how I pre-processed this data, and then the architecture of my module, building the module. Then maybe I'm going to discuss the learning rate as a hyperparameters involved in this module, and the other fixed parameters, the other parameters that I fixed within the module. I'm going to be showing two different modules for sure. One is they are going to be very much identical, only the learning rate will change between those two modules, and thus I'm going to look at the results in terms of accuracy and in terms of the loss that I get after fitting the module. And then I'm going to present some further work that one can do to learn more about fitting modules. All right, let's go ahead. So what is the problem and what is the proposed solution? The idea is that we, in all modules, reaching high accuracy in image classification is very crucial in many fields, right? So we use image classification in several fields, a variety of fields. We can talk about healthcare, politics, economics, and so on and so forth. So the idea is that we always need high accuracy when we are building the modules and when we are fitting the modules, right? We have sometimes little data, however, and thus it's very difficult to reach sufficient accuracy sometimes. Now, the data I'm going to be presenting today is the CIFAR 100, popular CIFAR 100 data. It includes 60,000 images. This data, we can say relatively, we have little data comparing to the number of to classifiers, the number of outputs that we have, right, or number of classes that we have. I'm going to get to that later, right? So we have a problem with little data sometimes. If we have little data, then it's difficult to reach high accuracy. The solution to this problem include, right? The solutions include, but not exclusive to, probably you want to change the batch size of your module. Probably you want to add more layers to get more accuracy, right? If you are using the neural network model. Probably you want to see the effects of the changing rate, right? When you use optimizers in your modules. And then the last one is the one that we're going to check in here, right? So we're going to check the effects of changing the learning rate on the accuracy and the loss of image classification model. All right, let's go ahead. So the data set that I'm using is the CIFAR 100 again. The CIFAR 100 includes 60,000 images, all 32 by 32 colored images, right? You can refer to the website to check those. The images are organized in 100 fine labels, right? So the images are having 100 fine labels, right? So that we have 600 images for each of those labels. Each of the fine labels have 600 images, right? So imagine we have 100 fine labels multiplied by 600, that gives us 60,000 images. Some of those, I'm going to give examples of the fine labels. You can be looking at beaver, dolphin, camel, or hamsters. Those are some examples of the fine labels that exist in the CIFAR 100 data set. Apart from the fine labels, there's also the gross labels of the data set. That refers to the superclass of the images, right? So we can see some superclasses such as aquatic mammals, flowers, large omnivores, or herbivores, right? So these are the coarse labels or the superclasses of the images, and then we have the fine labels. Mainly, we're going to be working on the fine labels for the modules that I'm going to be showing today. Right? So we're going to focus on fine labels for those images. All right. So these are some examples of the images. These are the first 16 images in the CIFAR 100 dataset. You can see a cow kind of sorta. It seems like a cow in here. We probably have a dinosaur in there. Probably have a telephone, an elephant in here, a keyboard in a hand, a cup, something like that. So this is a little bit of exploring the data, right? So this is part of the images in the CIFAR 100 dataset. And then how did I do the pre-processing of the data? I'm going to say that please refer to the links that I have down there to get to my code on my GitHub, right? I'm going to leave it in the comments below. So you can get to see how I built those modules. So pre-processing the data included modifying the data type, right? So I changed it using two categorical. This is the function that I used. So the image classes vectors were converted to binary classes matrices using two categorical. I'm using Keras for my work. And then I did some scaling and normalization. So data were converted to 32-bit floats, right? And then next, the input features were scaled between 0 and 1 by dividing by 255. Please refer also to my to the code to see how I did the pre-processing of the data. In the end, data augmentation and pixel scaling techniques were implemented. And mainly what I implemented was sample-wise centering, image whitening through CCA transformation, and then random flips along the horizontal axis, right? So we're flipping the images, we're augmenting the data so that we can get more accuracy. So different types of scaling techniques that I used. You can probably add more as further. Now building the module. The module that I worked on is the CNN module. It's a sequential module, and I arranged this CNN module in stacks, right? So the module in here, or my module, consists of 18 constitutional layers, right? I have 18 constitutional layers arranged in layers, units, receptive, and this is how I arranged them, right? So we see layers, units, receptors for each one of them. Please refer again to my code on my GitHub to see the architecture of the module. And the activation layer used for all through the module, all through the CNN module, is the ELU in Keras activation function. This is the function that I use. I'm not going to get to explanation of all of that. You can refer to that online. All right, go ahead. So what did I mainly do? I focused on changing the learning rate. So what happened to the learning rate and the other parameters? So I have two modules in here, and I compared those two modules. Both of the modules were very identical. However, the learning rate values used in the optimizers, right, were different. So the learning rate for all module, the optimizer is stochastic gradient descent for both modules, and the learning rate was fixed to 0.1 in one module. The learning rate for the stochastic gradient descent for the other modules decreased by 10 factor after the 34th iteration. That means after 34 epochs, the learning rate decreased by 10 factors in there. So how did that affect the performance of the module? This change in the learning rate for the second module, how did it affect the performance? Let's go ahead and check. Let's see first the other parameters. So the batch size were fixed in both modules to 100. The dropout was 0.5 in both modules. The L2 decay rate was 0.0005. The crop size is 32. The momentum rate for the optimizer is also 0.9. These are the other fixed parameters. Okay, stochastic gradient descent again was chosen for while compiling the module. Random cropping was applied to the module before training, and categorical cross entropy is used for the loss function. Please refer again to my code to see all that. Let's see the results now. So again, I compared the two modules. One had a fixed learning rate, one had a changing learning rate. So let's see the accuracy in here. If you look at the accuracy for the first module, where the learning rate was fixed, remember, to 0.1, the accuracy seemed to very much increase. At some point, it reached about 0.42, 43, something like that, after about 50 epochs, right? For the second module, when the learning rate changed after the 34th epoch, you can see here that the accuracy increased both on the training and test set up to the 34th epoch, and then it decreased sharply. I got increase in the accuracy of the module. So the changing rate, I can simply say that the changing rate in my second module affected the accuracy of my module. That's in terms of the accuracy. So I can say that the changing the learning rate after the 34 epochs pretty much helped increase the accuracy on both the training and the test sets. Let's get to the other results. The other one is I compared also the loss results, that were the loss of the module. So you see here the loss of the module for the first module, it decreased. For the second module, it also decreased very much after the 34 epochs. So changing the learning rate also helped in terms of the loss of the module. Further work can be trying different functions for the learning rate. So I tried changing the by a factor of 0.1. You can try by 10, sorry. You can try different other factors. You can try at different epochs while doing the module. I tried the 34 epoch. You could probably try 35, 100, or whatever epochs you change that, and then you do you check the accuracy again and the loss function. Pretty much that's it. Thank you very much.